Hello AP Physics students, it's Mr. Kennedy here. I hope you're all doing well. Today we got a little video lesson here on inductance. And we're going to really take a look at three things here. We're going to look at mutual inductance, we're going to look at transformers, and then we're going to look at self-inductance. And you're going to see that mutual inductance and self-inductance are actually really closely related. And transformers is just a version of mutual inductance that you actually did last year. But we are talking about inductance here. Talking about currents that are induced in one based on another or inside of itself. So let's take a look at a really simple example here. And this is the beginning of a transformer. But let's say we take a look at a piece of iron. Just imagine a bar of iron right here. And if you've got a bar of iron, and what I do is I wrap some coils of wire around this little side here, and this is going to be attached to a power supply, and then this set of coils of wire, these are complete coils too, this little set is not going to be attached to a power supply. So this one's going to be attached to a power supply and this one is not. So let's look at what happens when we actually turn on this one. And in this first part, we're talking about DC current. I'm talking about direct current. I turn it on and we see what happens. So let's say we turn on some direct current. So right now there's no current flowing in, there's no current flowing here, there's no magnetic field inside there, and now we turn this current on. We turn that current on and now current begins to flow. Current begins to flow, and now because of that, there's a magnetic field running to the right inside of this magnet, or the inside of this iron, which becomes a magnet. The domains line up and it becomes a magnet. Well, now if you think about it for a minute, there was no magnetic field going through these loops, and then there was some magnetic field going through these loops. So there was a change of flux going through this loop going this way. So we started with no flux, and then we started flux going this way. But because of that, that means current will be induced inside of these coils backwards that is going to produce a backwards voltage and a backwards current to oppose the change that created it. There was a magnetic field that got bigger going this way. It creates a magnetic field going bigger that way, so the current flows this way around there. So, but because this is DC current, it's only going to happen for an instant. Because once this actually stops changing, once there's a change that's no longer there, then it's going to stop happening. And the actual relationship that happens here is this. The EMF, the voltage, remember EMF is just voltage, is negative M times the change in current over the change in time. M is called the mutual inductance. This is called mutual inductance and is measured in henries. And 1 Henry equals 1 joule per amp squared. So what this shows you is that in this coil, a voltage will be induced the more the current changes. The key is that there is a change that has to happen. M is just the relationship. The mutual inductance really depends on the number of coils that are involved and what the area of the spacing is and what mu naught is and what mu of the material is. All of those things are what's coming in there. That's not really something that's addressed very well in the AP curriculum, but it's something that'll come up probably in your next course on electricity. So again, because there was a change in current, here, this is going to have a change in current. It went from nothing to something. Then this will induce an EMF backwards, and that's why there's a negative sign right there, based on the parameters between them. So again, this is the change of this current producing an EMF in this coil. Now, we said we use DC current in the beginning, but that's not really a good idea because DC current is only going to change once. It's only going to happen when we first turn it on. Now, oddly enough, when we turn this off, when all of a sudden we turn this off, see, once we have this turned on, this will stop having current flow there because there's no change. But then once we try to turn it off, now it will try to produce a current that points with a magnetic field pointing the same direction because it doesn't want to turn off either. But direct current is not something that you would typically use for this, because if you use alternating current, then what happens is this has a constantly changing magnetic field. So it's going this way, then this way, then this way, then this way, which means there's a constant change that's happening in this coil, which means this is constantly being having a current induced. Now, one of the things you saw last year with transformers is because you would see that this has less loops than this, then the voltage produced in this side of coils would actually be larger than the voltage that's produced here. And we'll see that in just a minute with transformers. But again, in inductance, this coil, in mutual inductance, this coil is producing a magnetic field, and because of that magnetic field is changing, is producing a changing flux in this coil, which induces current and voltage in this coil based on this. The change in current times the mutual inductance, which is again just some constant, tells you the voltage that comes out here. So this same thing happens in a device called a transformer. In a device called a transformer, what you have is some kind of iron core, right here. And then wrapped around the iron are going to be coils of wire. And we'll have them wrapped around the other side too. Now, what's happening inside here is mutual inductance. We would say that this is the primary coil and this is the secondary coil. This is where we put the input, this is where we put the output. Now, it makes sense to use alternating current here because we want a constant change. So what happens is this has a current that flows one way, then flows the other way, then flows one way, then flows the other way, back and forth, keep alternating. And because of that, that means the magnetic field goes up and down through this piece of iron. But because of that, that means the domains are going to line up, and they're going to line up with a magnetic field this way, then a magnetic field this way, then this way, then this way. So this set of coils is going to induce a current. And this is pretty amazing when you think about it, because this set of coils and this set of coils never touch each other. They don't touch each other at all, but they're able to communicate an electrical idea between them. Now, what happens is that the number of turns in the primary and the number of turns in the secondary, this is literally how many times it's wrapped up, is proportional to the voltage. So the main rule here is that the number of turns in the primary over the number of turns in the secondary is equal to the voltage of the primary divided by the voltage of the secondary. In other words, they're exactly proportional. Now, if you put in a low number here and a higher number here, that means the voltage will step up. That's a step up transformer. If the number of turns on the secondary is smaller, then it's a step down because the voltage will step down. Now, what typically happens when we start talking about this is someone will say, well, gosh, couldn't we just use transformers to make things run forever? We'll just keep stepping up the voltage and stepping up the voltage and stepping up the voltage forever. But the problem there is that the power, at very best, has to be the same. The power that comes in and the power that comes out has to be the same. But it's always going to be less than that because we're never going to have a perfect transformer anyway. But if the power is the same, if the power of the primary is the same as the power of the secondary, then that means that voltage of the primary times the current in the primary is equal to the voltage of the secondary times the current in the secondary, which means as the voltage goes up, that means the current goes down. So we see here that although you have the voltage going up with the number of turns, the current goes down in that same proportion. So this becomes IS over IP. So when the voltage goes up, the current has to go down by the exact same amount that happens with the voltage going up at the same proportion. So let's take a really simple example with this. And you did this last year, and this is overall a pretty minor topic with AP Physics, but it's one you should know anyway. So again, let's say that we have on a transformer, let's say we have 50 turns here, and let's say we have 100 turns here. And let's just say that we are putting 10 volts of alternating current on the primary side, that's what we're putting in, and 2 amps of alternating current on this side. Well, let's just see what happens. And this is a really simple example. So the number of turns doubled. That means this is a step up transformer. I'm stepping the voltage up because I'm stepping the number of turns up. So because the number of turns in the primary has to be proportional to the voltage, we see that this is a 2-to-1 ratio, so I'm going from 50 to 100, so the voltage must do the same thing. I'm going from 10 volts, so I must get 20 volts alternating current out of this one, because I've got twice the number of coils. But because of that, I'm going to have to pay for that by having my current drop. My voltage doubled, because that's what this is, a step up, but my current actually dropped by the same proportion. It drops by 1/2. So this is only going to be 1 amp alternating current on this side. Remember, proportions that we talk about for the turns is for voltage, not for current. For current, it drops down. But what you can see here is in the transformer, if you have 10 volts times 2 amps, we're going to have this as a 20-watt transformer, because that's voltage times current is power. So the power there is 20 watts. On this side, 20 times 1 is also 20 watts. And again, this is never going to happen in real life, because what you're going to see is that you're always going to have losses that's involved here. But simple thing with transformers, the number of turns is proportional to voltage, and it's inversely proportional to current. Whatever you gain in voltage, you're going to lose in current. And these are really useful devices, because what you can do is you can make your voltage be whatever you need it to be. Maybe you need it to be larger, so you can step it up for large distance transmission. Maybe you need it to be smaller for a small device inside your house. But these are very, very common devices. So, and again, the key here is to use alternating current. The weird part is we're getting to the point in the course where we're really on the edge of the things we're about to cover. The next thing that will be covered, which is not in the AP course, is alternating current. And you can see that that starts to creep up in transformers a little bit here. So transformers were an example of mutual induction. That's an example of mutual induction that happens. 2 coils inducing current in each other. But there's one last thing that we should talk about, and that's self-induction. And this is going to lead us to some things that we'll deal with in circuits as well. But imagine if you have that same iron piece right there, and now you've got a coil of wire around it. And we know this is just a solenoid. But this is probably one of the more fascinating things I think that I think about in physics. When I turn this on, when I put current through these coils, and let's just say for the sake of argument it goes around this way, producing a magnetic field, and to the right inside the iron. What's fascinating about this is because there was no magnetic field in the iron, and then all of a sudden there is a magnetic field pointing through the iron, a magnetic field that these coils created, what this is going to do is it is going to temporarily cause a EMF back in the other direction. So it induces an EMF in itself. That's why it's called self-induction. And for this, the EMF is negative L di dt. Same idea. This is still measured in henries. And 1 Henry is 1 joule per amp squared again. The more that this current changes, the more it induces a back EMF, backwards the other way, inside of this. So what happens is if you try to turn on a current in here, it is going to have the biggest change in in current, and therefore the biggest change in magnetic field and the biggest change in magnetic flux. And then what it'll do, it'll have the biggest change backwards. But then after a while, this comes into a steady state, the change no longer happens, and just current flows in this like it's a wire. So at first what it does is resist current, and then after a while, it lets that current through. But then, if we try to turn this off, it wants to keep producing a magnetic field in the way that it did. It wants to resist the change. So it will keep putting out current for a while to induce a current in the same direction that it was flowing when you try to turn it off. So when you try to turn this on, it flows backwards to resist it. When you try to turn it off, it tries to keep pumping out current in the same direction. And the reason is that it actually has energy stored inside the magnetic field. And that energy, the energy stored in the magnetic field, is 1/2 Li squared. 1/2 L times the current squared, L being the self-inductance. M was the mutual inductance, L is the self-inductance. And this is a pretty bizarre property that it resists changes in the flow that you have. Now, in one of my first years of teaching, I had some nice power supplies, but they had little fuses on them, and my students kept blowing the fuses. They were doing it deliberately. What they do is they just cross the wires, they turn the power up all the way across the wires across it, and then they blow the fuse out. And then I said, okay, that's it. If you guys are going to keep doing this, then I'll charge you for the fuses. Well, then the students would just say, okay, no problem. Here's my money for the fuse, and then they'd blow it out again. But what I did instead was I introduced something called a slow blow fuse to them. And a slow blow fuse, where a normal fuse looks like this, it just has a chamber there and there's a wire. And when that wire has too much current in it, it melts, and that's it. This whole device just shuts down or protects your circuit. That works great. But what I did is I introduced something called a slow blow fuse into the power supplies, and it worked great. Instead of just being a straight wire, the wire was curled, just like the idea of the curling of the solenoid here. So this would resist changes. So let's say the students would try to spark the current really high. Well, it would cause a back EMF or back current, at least temporarily, so it wouldn't blow out the fuse. It would just resist that change. And from the rest of the time, I didn't have another fuse that was blown out. One last thing. This coil, which we know is a solenoid, is also called an inductance coil. So solenoid and inductance coil are really the same thing. And what you're going to see is that they have properties of springs because they're kind of like electrical springs, and they're kind of like actual springs too, because they're just coils of wire. And I would claim that the coiling up wire turns out to be a really important invention to human history, because it became a spring, it became an inductance coil, it produces magnetic fields, all kinds of things that you can do with it that you probably didn't expect just by coiling up some wire. All right, so what we talked about today was inductance, that one coil will induce current in another, especially if there's a piece of iron or something to communicate the magnetic field between them. It helps to have alternating current with them, and we saw that in the transformer, that the transformer just, if you want to change the voltage, change the number of turns on each side. You want it to step up, increase the turns. You want it to step down, decrease the turns. And then we saw self-induction, that this will happen inside of a coil all by itself, that when you try to change the current in here, whether you try to turn it on or turn it off, it's going to resist those changes. All right, everybody, so you can start working on worksheet number 2. You can do pretty much the whole thing. And email me with any questions. And I hope everybody has a great day, and I hope everybody's doing awesome. All right, talk to you soon.